Alright, what's up everybody, Mr. Mira here, and today we have a Java video that we want to go over Big O runtimes. We're going to go over the various runtimes and talk about what causes each runtime to occur. So let's open up our file here, and I think we went old school movie name today. We did, shall we dance? So we have our public static void main string array of args, and we want to talk about the various runtimes, and the runtimes that we're going to talk about, I'm going to write them out here. We're going to go through these one at a time, starting with O of 1. Now, O of 1 is known as constant time. Constant time is seen in basic operations of math. So if I say like int num equals 2 plus 3, that's constant time. If I said times 2 times 3, 2 times a billion, constant time. If statements are also constant time. If I said something like if 9 is greater than 10, we could do our print. We'll just do our print. We'll just do a print. Wow, I can't type the print statement. We'll do the, if I stop hitting enter, print bigger, or whatever we need to do in there. Else, if I added an else in here, that's still constant time. If I try to access the index of an array, it doesn't matter what the index number is. If the array has it and I try to access that index number, that is a constant time operation. Anytime you have a literal number instead of the length of something in a loop. So if I say like for int I equals, or for int I semicolon I less than 100, I plus plus, that's going to be constant time, even though it's a loop, because it's always running 100 times. When I, instead of the length of a value, the length of an array or string or list or things like that. So that kind of makes up constant time there. The next one we have O of n. This is linear time. Linear time. Linear time is seen in for loops or looping over collections. So if I did have an array and I looped over that array, as that array got bigger or smaller, the number of steps needed to change to complete the algorithm would change as that array length changed. That is our linear time, our O of n. So I'm not going to write out the array part there. Maybe I will. Give me a second. We'll speed this up and then we'll come back and we'll see it. We're not doing much in here, but we're looping over the array, and every element in that array we're printing out. Could have done with a for each loop, but it still works here. So an enhanced for loop or whatever you want to call it. Anyways, but as this number grows, as I put more elements in here, it's going to take longer. If I put smaller elements in here, less elements in here, I should say, it'll take shorter. So as n changes, the length of the array changes, the runtime changes when we have linear time. Next up, this is polynomial time. So n squared, so the caret n squared, computer squaring there. So polynomial time. Now this is seen if I have nested for loops over a collection. It's a pretty terrible runtime to achieve. So if you have to do it, you should really try to avoid doing it, we should say. But if you have to, then, there's not much you can do about it. So if I had another inside here, if I did another loop, I said for int j less than or array plus 2, j plus plus, and inside there, I printed out. So this is taking our polynomial time, it's n squared. So whatever this is to run through this entire algorithm, we square it, whatever that length is, and that's how many steps we need to do it. So that's a pretty terrible thing to have, but like I said, if you can't avoid it, then that's what you're looking for. But if you see nested loops over the same collection, I have to stress that, ARR2, same collection, then it's squared. Different collections, then it's not squared, but same collection and it's squared. This is exponential time. I'm not going to write out an example for here. The most common place you see this is in recursion. It also comes up in binary trees, which we'll look at a later video, but recursion's a big one that is exponential time. So again, sometimes, you might want to do things recursively or whatever, but just know that it can have an impact on your time complexity. It can have a pretty serious impact on your time complexity. This runtime here is very dependent on other conditions, but it's very bad if your conditions aren't the greatest. So it can get out of control very quickly. Then we have log n. This is logarithmic time. Oh, if I could spell logarithmic time. That looks right. And this is seen when searching. This is commonly seen when you're doing searching, like binary search. The time grows in proportion to the logarithm of the input. So remember, it's base 2, log base 2 is what you're looking for there. So I'm not going to write out like binary search, but that's kind of when you see that happen. And then maybe we'll do, or there is another video on binary search. I got to think about what's got to go in the basic playlist. This is the medium playlist or whatever we want to call it. But if binary search isn't in the basic, maybe we'll do it here. The last one is n log n. This is just n log n time. This is commonly seen in sorting algorithms. We're definitely going to see sorting algorithms coming up here that have n log n time, and we'll examine more closely there what happens in those instances to give us n log n as our timing. There we have a very, very quick overview of the runtimes that we commonly see when dealing with Big O notation and how we interact with them and how we see them. The key takeaways here, besides the exponential, the logarithmic, and the n log n, knowing constant time, knowing linear time, polynomial time. If you have different collections, right, I'll just make this to end it here. If we have different collections, it's actually O of n times m or n plus m, right? So you might see like that, or you'll see O of n times m. So I'm not saying nested for loops give you both of these results, but if you have two different collections, right, whether you're doing linear time and then down below this, I loop over a different collection, or if I'm doing nested, right, I multiply. But if I have multiple different collections going on here, I add them together. So you see different runtimes on different collections mean different things. So you could also have those as well. Those come up quite frequently. And there we have that video, that little ending there. And then next time we'll see what comes up. But until then, everybody have a week.